This is section 5.4, Logarithmic Functions and Models. These are the topics we're going to cover. We're going to first start by defining what a common log is. A common log of a positive number x denoted by log of x is defined to be log of x equals k if and only if x equals 10 to the k, where k is a real number. Notice that k equals log of x. So if we were actually looking for what k was and we knew what x was, we could actually solve this. Logs are very important because logs actually give us exponents. Evaluate the following. Log of 10. We know log of 10 is actually equal to 1 because 10 to the first equals 10. Remember, x equals 10 to the k. This is what k is. K is that exponent. So log of 100. My base is understood to be 10. 10 to what power is 100? 2. 10 squared is 100. Log of 1,000 is 3 because 10 cubed is 1,000. Log of 10,000 is simply 4 because 10 to the 4th is 10,000. We get into some interesting ones. Log of 1/10. This is actually negative 1 because 1/10 is 10 to the negative 1. Log of 1/100th is negative 2. And log of 1 is simply 0 because 10 to the 0 is 1. If we actually do the graph of log of x, here's the graph of y equals log of x. Here's the graph of y equals 10 to the x. These are numbers we got from the prior slide. If I throw in here this line y equals x, notice that this graph y equals 10x and y equals log of x are mirror images of each other. And we know from our prior study of inverse functions that the graphs of inverse functions are mirror images of each other, so y equals log of x and y equals 10x are actually inverse functions. And this gives us our inverse properties of common logs. If I have f of x equals log of x, then I know f inverse of x equals 10x. Therefore, if I did the composition of functions, I know f of f inverse of x has to be equal to x for all inverse functions. That means log of 10x has to be equal to x, and 10 log of x has to be equal to x as well, because that's what the composition of these two functions give us. Let's see how we can apply this. Say I have 10x equals 75. I'm going to take the common log of both sides because I know logs give me exponents. So log of 10x equals log of 75. Well, this is base 10, understood to be base 10 when I don't write the base. So log of 10x is simply equal to x because we know log and 10x are actually inverse functions, so they undo one another. So x equals log of 75. I'm going to use our calculator, and so I get x is 1.875. I can also approach other types of questions, like log of x equals 3.4. I'm just going to basically exponentiate both sides using base of 10. So 10 to the log x equals 10 to the 3.4 power. Now 10 to the log x should just give us x based on 10 log x equals x on the inverse property we looked at a second ago. And then I'm just left with x equals 10 to the 3.4 power. Once again, we're going to use our calculator, and we get x is 2,511.886. Now, this would be nice if every time we had a number it was base 10, but we don't always have base 10 numbers. So base 10 is our common log. However, we have other logs, logs of base a. And we can define log base a of x equals k if and only if x equals a to the k. Remember, we didn't have the a before. It was not, nothing was listed there, and if nothing's listed there, it's understood to be base 10. So if I were to list 10 here, this would be log base 10 of x equals k equals x equals 10 to the k power, which is exactly what we had before. Let's see how this works. Let's switch in between statements. I have y equals b to the x and log base b of y equals x. This is just switching between equivalent forms. We call the b our base in this case, and b the base here as well. So log base 4 of 64 equals 3. The equivalent expression would be my base is 4, my exponent is 3, because logs give us exponents. 64 equals 4 cubed. That's a true statement. Log base 5 of 25 equals 2. My base is 5, my exponent is 2. So 5 squared equals 25. That's also true. Log base 4 of 8 equals 2. Base is 4, exponent is 2. 4 squared equals 8. That's not true because 4 squared doesn't equal 8. That's false. Log base 36 is 6 equals 1/2. My base is 36, my exponent's 1/2. So 36 to the 1/2 power equals 6. That is true as well. I can evaluate these expressions. Log base 7 of 49, we know this is 2 because I know 7 squared equals 49. Log base 2 of 32 is 5. Remember, logs give us our exponents because 2 to the 5th is 32. Log base 5 of 1 over 25. 1 over 25 is the same as 1 over 5 squared, which is 5 to the negative 2 power, and 5 to the negative 2 power is 1 over 25, so my answer is simply negative 2. We have something called the natural log function. This is f of x equals ln of x. This is the other one you will see on your calculator. Please realize when you see ln of x, this is just log base e. That's the same e we touched on in the last section. The natural log of e is simply 1 because e to the 1 is 1. E to the 1 is e. Natural log of square root of e is 1/2. Natural log of 1 is 0. In fact, the log of any base, no matter what the base is, the log of 1 is always going to be 0. The inverse of f of x equals log base a of x. Just like the inverse of log of x was 10 to the x, the inverse of log base a of x is y equals a to the x. Therefore, our inverse properties have to hold here as well. Log base a of a to the x equals a. So if your base down here matches your base inside, all you're left with is the exponent. Similarly, a to the log a x equals x. So if your base out here matches your base for the log, they basically cancel each other. Let's see how this works. 4 to the x equals 256. I'm going to hit both sides with log base 4. Log base 4 of 4 to the x, the base is matched, so I'm just left with x. So log base 4 of 256. Now we cannot use our calculator here because we know on our calculator we only have base 10 and base e. So I'm going to rewrite 256 as 4 to the 4th power. Now I know the base here on the log and the base inside match, so I'm simply left with the exponent, which is 4, the same property I used to get the x here. Log base 3 of x equals 1.4. We're going to raise both sides, we're exponentiating both sides using base 3. This is going to give me 3 to the log base 3 of x equals 3 to the 1.4. The bases match, and we're simply left with x equals 3 to the 1.4 power, which is 4.656. And our last one is base e. E to the x equals 98. I'm going to take the natural log of both sides. This log base a of a to the x still applies because natural log stands for base e. The base is matched, so I'm just left with x on the left-hand side equals the natural log of 98. And we can use our calculator again in this case because we have natural log. And the natural log of 98 is 4.585.